Hello. All of you, am
Good
I
evening.
audible?
Yes, sir.
Okay. So today we'll start the physical chemistry class, and the course code is MCH-013. So in this physical chemistry class, we'll start from Gibbs. We'll start from Gibbs-Helmholtz function, because in the thermodynamics you have already studied in your BSc level what are the different types of functions, internal energy, enthalpy, first law of thermodynamics, second law of thermodynamics, all the things you have already studied. So in this postgraduate level, we will start from entropy and the criteria for spontaneity of the process. So for this, we'll discuss, first we'll discuss why entropy, what is entropy, and what are the different criteria for spontaneity of thermodynamic processes. Before that, we should know that what is spontaneous process and what is non-spontaneous process. All the things you have already studied. So the spontaneous processes are the processes which proceed automatically without any type of external force. And again, the spontaneous processes are divided into two types. The first one is spontaneous process which require initiation, and the second one is the spontaneous process which do not require any type of initiation. That means the first category of spontaneous process are the processes you just initiate the process and after that automatically that will continue. And the second category of spontaneous processes are the processes which do not require any type of initiation. And the non-spontaneous processes are the processes which will continue by continuous supply of energy, and if you stop the supply of energy then the process will stop. And here we will discuss what are the different criteria for spontaneity of process. So here we will discuss from your study material. So you can see we will begin the unit by discussing difficulty in using entropy change as a criteria for spontaneity of thermodynamic processes. So here we will establish the need of new state function predicting the spontaneity based on the properties of the system only. Therefore, we will take the processes occurring under the constant temperature and constant volume condition. That means for these processes, so for to define the new function, we will take the processes occurring under the constant temperature and constant volume condition, and here the new state function is called as Helmholtz energy, right? So then after that we will work out the criteria for spontaneity of the processes occurring under constant temperature and constant pressure condition. So first let us come to Helmholtz function. In your earlier classes you have learned about the various aspects of energetics and first law of thermodynamics, all the things, internal energy, enthalpy, all the things you have already studied. So you have also learned about the spontaneous processes. So here that is the spontaneous processes, the processes that occur on their own under a given set of conditions without the aid of any external agency. So this is spontaneous process, the processes that occur on their own under a given state of condition without the aid of any external agency. And the non-spontaneous process are the processes which will occur by continuous supply of energy from external agency. Now, before going to define new state functions, that is served as the criteria for spontaneity, because in the graduation level you have studied that entropy is not the sole criteria for spontaneity of the process, or enthalpy is not the sole criteria for spontaneity of the process. So here we will define a new state function that will serve as the criteria for spontaneity of the process. Now before going to that, before going to define the new state functions that serve as the criteria for spontaneity of the process, we should discuss two important relations that would help us. So first we should discuss two important relations, and these two important relations will help us to derive or to define the new functions that will help for spontaneity of the processes. So the first one is Clausius inequality. Clausius inequality. Now let us consider two processes. So starting from this, your course will start. So the first one is, so before going to the criteria of spontaneity, before going to defining the new state function that will serve as the criteria of spontaneity of any type of physical processes, first we will discuss two important relations, and this is the first one. The first relationship is Clausius inequality. Now let us consider two processes taking place between same initial and final stages. That is, we will go from stage 1 to stage 2 by two different routes. So these are the two different routes. Here the initial state is state 1. You can see this is the initial state, that is state 1, and this is the final state, that is state 2. So from initial state to final state, we can go by two different routes. We assume that one of the processes takes place under reversible condition and the other takes place under irreversible condition. So the two different routes from state 1 to state 2 are, these are the two different routes from state 1 to state 2. Out of the two different routes, here we will assume that one of the route here we will assume that one of these processes takes place under reversible condition and the other one will take place under irreversible condition. And since internal energy is a state function, the change of internal energy of those processes will be equal. So this is state 1, this is route 1, and this is route 2. For state 1 to 2, for moving state 1 to 2. So there are two different routes. Out of the two different routes, here we will assume that one of the route will be carried out under reversible condition and the other route will be carried out under irreversible condition. But you can go from state 1 to state 2 by the above two different routes. The two different routes are A and B. Either A may be reversible or one of the two different, from one of the two different routes A and B, one will be reversible and other will be irreversible. And again we know that internal energy is a state function, that is, it is independent upon the path followed. It will only depend upon the state 1 and state 2. So as the internal energy is a state function, if we will go in the reversible route, the change in internal energy will be du reversible, and if we will go by irreversible route, the change in internal energy will be du irreversible. And as internal energy is a state function, for both the route, the change in internal energy will be same, and hence du reversible equals to du irreversible. This is equation number 1. And again you should recall the first law of thermodynamics. The equation for first law of thermodynamics is du equals to dq plus dw. And in terms of first law of thermodynamics, we can write this equation if we use, so this is the mathematical statement of first law of thermodynamics, and if we apply this mathematical state of first law of thermodynamics to equation 1.1, we can write dq reversible plus du dw reversible, dq reversible plus dw reversible equals to dq irreversible plus dw irreversible. And now if we rearrange these expressions, we can write So that means we will take dq to one side and dw to another side. If we rearrange this expression, we can write dq reversible minus dq irreversible equals to dw irreversible minus dw reversible. And here the dw represent work done on the system, and we know that work done on the system is positive, and its magnitude during the reversible process is greater than during the irreversible process, because here dW is the work done on the system, and in chemistry we are considered that work done on the system is the positive work, and work done by the system is the negative work. So here we are considering dW is work done on the system, so that here that is the positive one, and the magnitude during the reversible process is more than the magnitude of work done during the reversible process is more than the work done the is more than the magnitude of work done during the irreversible process. That means the reversible work is more than the irreversible work done, and hence the magnitude of dW reversible is greater than magnitude of dW irreversible, that we have studied from the intermediate level. So this is equation number 1.5. Now, so if we apply this condition to the RHS of equation number 1.4, so this will give rise a negative value. That means rearranging we get dW irreversible minus dW reversible is greater than 0. Now substituting this value in equation 1.4, if we put this value in equation 1.4, we can write dq reversible minus dq irreversible is greater than 0, and here so this is equation 1.7. So in equation 1.7, if we divide the absolute temperature T, we can write dq reversible by T minus dq irreversible by T is greater than 0. And again from the intermediate level, we know that dq reversible by T is nothing but that is called change in entropy, so that is ds. So if we put these values in equation 1.8, we can write ds minus dq irreversible by T is greater than 0, or simply we can write ds is greater than dq irreversible by T. Now combining the expression for entropy change during reversible and irreversible condition, we can write ds is greater than equals to dq by 2. So from this condition, we can write ds is greater than equals to dq by T. So this expression is known as Clausius inequality, and this expression will be used later to arrive the expression of spontaneity of thermodynamic process under different conditions. But in the semester question, you can find out derive the expression of Clausius inequality, that is ds greater than equals to dq by T. Are you getting or not? Hello? Hello?
Yes, sir.
Okay. Now coming to the combined first and second law. So this is one type of 5 marks question, derivation of Clausius inequality. You have to derive by this way what we have discussed here. Now coming to the combined first and second law, that is the fundamental thermodynamic equation. So here we will find out or derive the fundamental thermodynamic equation. And in order to derive the fundamental thermodynamic equation, let us again consider the mathematical statement of first law of thermodynamics, and that is du equals to dq plus dw, and consider a case or a process of a closed system containing gas having constant composition and undergoes a reversible change in such a way that only work of expansion is permitted. That means here we will consider a process occurring in a closed system where the container contains only gas, and reversible changes will be there, and only work of expansion is permitted. So work of expansion means work is done by the system on surrounding. In the previous one, we have discussed work is done on the system. Here we are discussing work of expansion. That means the system will expand, and hence that is considered as work is done by the system on surrounding, and hence that is considered as negative work. Since we are considering a reversible expansion, the opposing pressure would be equals to the pressure of the gas. So as we are considering the reversible expansion, and here the opposing pressure, that is the P external, will be considered to be pressure of the gas, and hence we can write dW equals to minus P del V. Here the negative sign represent work is done by the system, so that's why we have given a negative sign. If work will be done on the system, then that will be positive work. Therefore we can write dW reversible equals to minus pdv. And here from equation 1.9 already here so this one from equation 1.9 we know that ds equals to dq reversible by t, and hence we can write dq reversible equals to tds. This is equation 1.13, and this is equation 12, this is equation 13. Now combining, now substituting equation 12 and equation 13 in equation 2. So here this is first law of thermodynamics equation 2. So the first law of thermodynamics, the mathematical form of first law of thermodynamics is du equals to dq plus dw, and here we are writing the value of dw from equation 12 and writing the value of dq from equation 13. Putting these two values in equation 2, we can write du equals to tds minus pdv. This combined expression of, so this is the combined expression of first and second law, and that is called fundamental thermodynamic equation. So this equation is called fundamental thermodynamic equation, du equals to tds minus pdv. That all these things you have to remember. Now coming to limited utility of entropy change as the criteria of spontaneity. So here we are coming to criteria of what is the criteria for spontaneous process. Let us take up this question of limited utility of entropy change as the criteria of spontaneity. You will be studied about the entropy and spontaneity in your earlier classes. You have already studied. Now from the earlier classes we will take another expression, so that is called change of entropy of the system plus change of entropy of the surrounding, that is equal to change of entropy of the universe. That means del S system plus del S surrounding, which is equals to del S universe, is greater than 0. So it's meaning that the entropy of the universe is regularly increasing, that we have studied in our intermediate level. Entropy of the universe is continuously increasing. And here for reversible process, del S system plus del S surrounding, that is del S universe, equals to 0. Because we know that all the naturally occurring processes in the universe are irreversible process, that we have also studied from intermediate level. All the naturally occurring processes are irreversible process, and and are spontaneous process. So for spontaneous or irreversible process, the total change of entropy of the universe is greater than 0. That means the entropy of the universe is continuously increasing. And here, but for reversible process, the entropy of the change in entropy of the universe is equals to 0. And here we will discuss about the criteria of spontaneity. So first one, so these are the two relations we have discussed. So after discussing the two relations, here we will discuss the criteria of spontaneity and equilibrium. So in order to discuss the criteria of spontaneity and equilibrium, first we will discuss the Helmholtz energy chain. The first condition, that is called Helmholtz energy chain. Now, in order to discuss the Helmholtz energy chain, again we'll discuss the first law of thermodynamics, the mathematical form of first law of thermodynamics, where the where a process involving only mechanical work and the change in internal energy is given by the expression du equals to dq plus du equals to dq plus dw, and here we are discussing the work of expansion, so that's why in place of dw we are writing minus pdv. So the equation of the mathematical statement of first law of thermodynamics can be written as du equals to dq minus pdv. Now let us the consider Now let us consider the process where only heat flow is taking between the system and surrounding and no mechanical work is involved. It implies that in this case the volume is kept constant, that is dV equals to 0. So as the heat is flowing from the system to surrounding without any mechanical work, as there is no mechanical work, that means no pressure volume work will be there. No mechanical work means no change in volume, because mechanical work is nothing but the pressure volume work. So that means either the pressure will increase, the volume will decrease, or the pressure will decrease, the volume will increase. But here there is no mechanical work means there is no change in volume, so the change in volume dv equals to 0. So applying these values, the equation 17 will be converted into du equals to dq. Now again, according to the Clausius inequality we have discussed in the starting, that is Clausius inequality, ds is greater than equals to dq by t. And here putting these values, we can write tds is greater than equals to dq, so that we can write, now this is equation 18. From equation 18 we are finding du equals to dq, and again from equation 19 we are finding tds is greater than equals to dq. That means tds is greater than equals to du, or du is less than equals to tds. By combining this equation 18 and equation 19, we can write du is less than equals to tds, or we can write du minus tds is less than equals to 0. Now since u and s are state functions, so u is internal energy, s that is entropy. So both are state functions, and a combination of the two functions will be also gives rise a new state function. And here we can introduce another new state function, that is called Helmholtz function, in the honor of the German physicist Hermann L. F. Helmholtz. So here from this value, so here we are getting du minus tds is less than equals to 0. U is one state function and s is an state function. So by the combination of these two, that will give rise a new state function a, that is called Helmholtz function, capital A, that is called Helmholtz function. And here after observing this equation 20, we are writing that the Helmholtz function a equals to u minus ts, and the unit of the Helmholtz function, that is so that is the dimension of energy, right? So that is equals to joule, because we know that here u is in the form of joule, t that is in Kelvin, and entropy is joule per Kelvin, and finally we will find the value of a, the unit of a is in joule. Now Helmholtz function A will have the dimension of energy. The Helmholtz function A will have the dimension of energy. Therefore, it is also called as Helmholtz energy, and its SI unit is joule. When the process is carried out under constant temperature condition, the change in Helmholtz energy is given by the expression dA equals to du minus tds. So from this equation we can find out dA equals to du minus tds if the process will carried out at constant temperature. This is equation number 22. Now this is equation number 20. Equation number 20 is du minus dds is less than equals to 0, and equation number 22 dA equals to du minus dds. That means at constant temperature and constant volume, dA is less than equals to 0. So this represents constant temperature and constant volume. So dA at constant temperature and constant volume is less than equals to 0. We have initially assumed a spontaneous heat flow at constant volume and have applied at constant temperature in the condition of equation 21. Thus, equation 23 provide a criteria of spontaneous and equilibrium process, spontaneity and equilibrium for a process taking place at constant volume and constant temperature. So this is the criteria. So this is one of the criteria for the spontaneity and equilibrium of a process taking place at constant volume and constant temperature. Thus, under the condition of constant volume and constant temperature, a process will be spontaneous if the process will accompanied by decrease in Helmholtz energy. So this is the criteria. So this is one of the criteria of spontaneity of a process. Again, I am repeating. Thus, under a condition of under the condition of constant volume and constant temperature, a process will be spontaneous if it is accompanied by decrease in Helmholtz energy. So this is one of the criteria of spontaneity of the process, and we will continue to be so till there is a decrease in Helmholtz energy. So up to so till there will be decrease in Helmholtz energy, the process will be spontaneous. And when it reaches a minimum Helmholtz energy such that there is no further change, that is del A equals to 0, the system will be in equilibrium. That's why that is called del A at constant temperature. So D at constant temperature and constant volume is less than equals to 0. So till the process will be spontaneous, there will be continuously decrease in the value of Helmholtz free energy, Helmholtz energy, till the process will be, till the process will be spontaneous. There will be regular decrease in Helmholtz energy, and hence del A is less than 0. And when the Helmholtz energy will reach a minimum value, then there will be no further decrease in that value. In that condition, del A will be 0, and that is called the state of equilibrium. Combining both the conditions, that is decrease in Helmholtz energy and state of equilibrium, the criteria for the one of the criteria for spontaneity of the process will be del A at constant temperature and constant volume. So this is called del A at constant temperature and constant volume is less than equals to 0. Now for a finite change, the equation 22, this one, dA equals to du minus dts, can be written. So if very small change, then we will use the derivative form, and for a finite change, we can write the equation 22, which was dA equals to du minus dds. But for a finite change, we can write the value del A equals to del u minus dds. And in the similar way, we can write the criteria of spontaneity and equilibrium, that is del A at constant temperature and volume is less than equals to 0. So this is one of the condition for spontaneity and equilibrium. For spontaneity, del A is less than 0. For equilibrium, del A is equals to 0. And the system will be equilibrium when there will be no change in energy, and hence del A will be equals to 0. So this is the equilibrium condition, and this is spontaneity condition, criteria of spontaneity. Now the criteria of spontaneity, that is del A is less than 0. We find that the spontaneity of the process, all of you understood or not? Hello? Hello? Hello. Hello. So the criteria for spontaneity is del A less than 0, and we find that spontaneity of the process at constant temperature and constant volume depends on the combination of change in internal energy and change in entropy of the system, and hence we can write the condition of spontaneity of the process del A is less than 0, and the condition for equilibrium of the process del A equals to 0. But as here we are discussing the condition of spontaneity of the process, so that is del A is less than 0. Now in place of del A we can write del U minus TDS. So here we are discussing for finite change. For a spontaneous process we can write del U minus TDS is less than 0. And let us see now, see whether and under what condition the process will be spontaneous for such combination of del U and del S. So first we'll discuss case 1, where del U is less than 0 and del S is greater than 0. In this case, the value of del U and TDS will be negative, and that will be negative for all temperatures. Hence, the process will be spontaneous at all temperatures, because the value of del A is equals to del U minus TDS, this one. And if del U is less than 0, that means del U will be negative. Del U is less than 0, that means del U will be negative. And del S will be greater than 0, and here minus sign is there. That means del S is greater than 0, and hence overall that will be negative also, because minus sign is there. And the total value will be negative at any temperature. So if this condition will be there, that means in the case 1, if this condition will be there, that is del U is less than 0 and del S is greater than 0, then the process will be always spontaneous at any temperature. That means at all temperature the process will be spontaneous. Now coming to the case number 2, where the case number 2 is del U is greater than 0 and del S is less than 0. So here del U is greater than 0, that means that is a positive value, and del S having negative value, but here another minus sign is there, then that will totally become positive. And in this case, the total value of del A, that is del U minus T del S, will be always positive, and hence the process will be never spontaneous. So in the condition case 1, the process will be always spontaneous, and in the case 2, the process will be never spontaneous. Now coming to the case 3, where del U is less than 0 and del S is also less than 0. In this case, del U will be negative, T del S will be positive, and the value is del U minus T del S. Del U is negative and T del S will be positive. So there is a chance the overall value may be positive or negative, may be 0, whatever may be. So if the magnitude of del U equals to magnitude of T del S, then the value will be 0 and the system is in equilibrium. So at this temperature, the system will be at equilibrium, and this temperature may be called equilibrium temperature, and that is calculated as T equals to del U, magnitude of del U minus divided by magnitude of del S. Such a process can be spontaneous only when the magnitude of del U will be greater than magnitude of T del S, because del U is negative. So if the magnitude of del U will be greater than the magnitude of T del S, then overall value will be negative, and in that condition the process will be spontaneous. This condition will be met at temperatures lower than the equilibrium temperature, and the process will be spontaneous. That means if the temperature will be low temperature, that means lower than the equilibrium temperature, in that condition the process will be spontaneous. Now coming to a temperature higher than the equilibrium temperature, T del S will be greater than del U and the process will be non-spontaneous. Now coming to another case, that is del U greater than 0 and del S greater than 0. In this case, both del U and T del S will be positive, and hence again one condition will be there. If the magnitude of del U equals to magnitude of T del S, then the system is in equilibrium. That means del A equals to 0. Now such a process can be spontaneous only when the magnitude of del U is less than the magnitude of T del S, that is magnitude of del U is less than magnitude of T del S, then the overall value will be negative and the process will be spontaneous. And if the magnitude of del U is greater than the magnitude of T del S, then the process will be non-spontaneous. Now coming to the case 5, when del S equals to 0. In such case, the process will be spontaneous only for exothermic processes and non-spontaneous for endothermic processes, because here del S equals to 0, that means T del S will be 0 and del A equals to del U. So for exothermic process, energy will be released from the system and del U will be negative. So the process will be spontaneous only for exothermic processes, that is del U is less than 0. Such a process will be equilibrium when del U equals to 0. Now coming to del U equals to 0. In such cases, the process will be spontaneous only when del S will be greater than 0. So such a process will be equilibrium when del S equals to 0. So now this is the condition of spontaneity and equilibrium for different combination of del S and del U and del S. So combination of del U and del S. So here if del U less than 0 and del S greater than 0, the process will be spontaneous and all temperatures and equilibrium not observed here, because del U less than 0 and del S greater than 0. So the value, this value will be always less than 0. So no equilibrium condition will be observed and the process will be spontaneous, because the value of del A will be 0, will be negative. Now in the another condition, this one, that is del U greater than 0, del S less than 0, the value of del A, that is del U minus T del S, is always positive and the process will be always non-spontaneous at all temperatures and no equilibrium condition will be observed. And in the third case, del U less than 0, del S less than 0, here the equilibrium condition will be observed if the magnitude of del U equals to magnitude of T del S. But for spontaneity, the magnitude of del U should be greater than the magnitude of T del S. So the equilibrium condition can be find out, the equilibrium temperature can be find out, that is T equals to magnitude of del U by magnitude of del S, and spontaneous at all temperatures lower than the equilibrium temperature. The process will be spontaneous at lower temperature, that means lower than equilibrium temperature. And similarly, this is the another condition where del U greater than 0 and del S greater than 0. So in this case, the equilibrium condition will vary if the magnitude of del U equals to magnitude of T del S. And here, as the magnitude of del U is less than magnitude of T del S, the equilibrium, the process will be spontaneous and at temperature higher than equilibrium temperature. But at equilibrium temperature T, the process will be in equilibrium, and we can find out the value of equilibrium temperature from this equation, that is T equals to magnitude of del U divided by magnitude of del S. And the other conditions are del S equals to 0. If del S equals to 0, only del U will be there. If del U will be less than 0, that is the process will be spontaneous, and that is only for exothermic process. And the another condition, del U equals to 0, that means del A equals to del S only, and the value of del S, if the value of del S greater than 0, the entropy must increase for a process to be spontaneous. So here one example is there. During an isochoric isothermal process taking place at 25 degrees Celsius, the internal energy of the system is decreased by 20 kilojoule per mole and the entropy increased by 50 joule Kelvin Kelvin inverse, mole inverse. Calculate the change in Helmholtz energy. So here the solution is very simple. Here it is given the change in internal energy. That means the internal energy decreased by 20 kilojoule per mole. So here we can write del U. The internal energy will be decreasing. That's why we will put a one negative sign. So del U is equal. The internal energy will be decreased by 20 kilojoule per mole, and hence del U equals to minus 20 kilojoule per mole. That means which is equals to minus 20 into 10 to the power 3 joule per mole. Because here we are converting the unit of internal energy from kilojoule to joule, because here the you can see the unit of the entropy is joule, Kelvin inverse, mole inverse. That's why we are changing the unit from kilojoule to joule. And here del S equals to 50 joule, Kelvin inverse, mole inverse, and temperature is given that is 25 degrees Celsius, which is equals to 298 Kelvin. Now applying these values in Helmholtz energy, del A, that is equal to del U minus T del S. And here we can find out substituting the values of T, del U and S, del S in the above expression, we can write del A equals to minus 34.9 Kelvin joule, Kelvin inverse, mole inverse, that is joule per mole. Since the Helmholtz energy has a negative sign, that means there is a decrease in energy of the process, and therefore that will be a spontaneous process. Now coming to the physical significance of the Helmholtz energy. So we know that dA equals to du minus TdS, and again from the first law from the mathematical statement of first law of thermodynamics, we can write du equals to dq plus dw, and for reversible process dq reversible equals to tds. So we can write du equal to tds plus du reversible, and putting these values in the mathematical statement of first law of thermodynamics, this one we can write dA equals to tds plus del u, dA equals to tds plus del w reversible minus tds. Now tds will be cancelled out, and dA equals to del w reversible, and this is equation 31. That is the sorry, that is showing the change of Helmholtz energy, which is equals to work done during isothermal reversible process, and hence the Helmholtz energy decreases, and the value del W reversible will be negative, indicating the work done by the system. Therefore, there is a decrease in Helmholtz energy equals to work done by the system during isothermal reversible process. This work includes all type of work of the system can do. Thus, Helmholtz energy change is related to maximum amount of work that can be obtained from the system, and that is known as work function. So this is the physical significance of Helmholtz energy. Now in the similar way, we will discuss another criteria for spontaneity of a process. The first one we have discussed, that is the Helmholtz function or Helmholtz energy, and the second one is Gibbs function or Gibbs energy. The second one is Gibbs function. Now here let us consider the spontaneous heat flowing taking place between the system and surrounding at constant pressure. In the previous one, we have discussed that heat flowing between the system and surrounding at constant volume. That means the pressure volume work will be zero. That means dV will be equals to zero. There will be no change in volume. Understood? Now here we are taking the another condition to find out or to define the statement of spontaneous process, that is heat flow taking place between the system and surrounding at constant pressure. Now here I will take just 2-3 minutes of break, and after that again we will continue. Okay. So here we will discuss another. So here we will define another function that will express the criteria of spontaneity of process. The first one we have defined, that is called Gibbs, that is called Helmholtz function or Helmholtz energy. The second one is Gibbs function. So in the Helmholtz function, we have considered a spontaneous process where heat flowing taking place between the system and surrounding at constant volume, that we have already discussed. But here, let us consider a spontaneous process where heat flow taking place between the system and surrounding at constant pressure. And hence, when heat will flow between system and surrounding at constant pressure, the change in heat or the heat flow is equal to change in enthalpy. That is, the heat flow is equal to change in enthalpy. That is, dH equals to dQ at constant pressure. dH equals to dQ at constant pressure. This is equation number 32. That is, change in enthalpy of the system. Now again, applying the same Clausius inequality that we have studied in the first part, the Clausius inequality, the ds is greater than equal to dq by t. Or again, we can write tds is greater than equal to dq. So if we apply the Clausius inequality to equation number 32, then the equation number 32 can be written as TDS. That means if we combine 32 and 33, we can write TDS is greater than equal to DH. Or again, we can write DH minus TDS is less than equal to 0. So here, again we know that means similar type of derivation is there. Again we know that DH is nothing but change in enthalpy and T is absolute temperature and DS is nothing but change in entropy. And here we find dH minus TDS is less than equal to 0, since both the enthalpy and entropy are the state functions. So the dH minus TDS will give rise to another state function, and let the new state function is called Gibbs function or Gibbs energy. Similar to Helmholtz function and Helmholtz energy, here we are defining new state function that is called Gibbs function and Gibbs energy in the honor of American chemist J.W. Gibbs, and it represented as G, and mathematically the Gibbs function can be defined as G equals to H minus Ts, and since H and Ts both have the units of energy, then also the Gibbs energy or Gibbs function, the SI unit of Gibbs energy or Gibbs function is Joule. And in infinitesimal change, for infinitesimal change, we are considering the derivative form, and for infinitesimal change, the equation can be written as dH equals to, dg equals to dH minus TDS, that is equation number 37. Now comparing equation number 35 and 37, so here this is 35, dH minus TDS is less than equals to 0, and here we are writing dH minus TDS equal to dg, and hence we can write dg at constant temperature and pressure is less than equal to 0. And here we can write a process taking place at constant temperature and pressure, the Gibbs energy change of the system is less than or equals to 0. Now coming to Gibbs energy, that is the criteria of spontaneity and equilibrium. In the similar type of derivation we will proceed. So here we know that TDS equals to dq reversible. That is from equation 13 we have already studied. And here from equation 32 we can write dH equals to dq, And comparing both the equations, we can write dH equals to TDS or dH minus TDS equals to 0. This implies that for a reversible process, dG equals to 0. So the LHS of the equation 39, that is dH minus TDS is dG. So dG equals to 0. That is for reversible process. And for an irreversible process, TDS is greater than dq irreversible. Now substituting this value in equation 37, this one, dg equals to dh minus tds, and putting this value in equation 37, we can write dg is less than 0. Since all spontaneous processes are irreversible, the equation 42 serves as a criteria for spontaneity of a process occurring at constant temperature and constant pressure. So, at constant temperature and constant pressure, the criteria for spontaneity of a process is dg less than 0. And similarly, at constant temperature and pressure, if dg equals to 0, the process is in equilibrium. Now coming to the relationship between spontaneity, Gibbs energy and entropy of the universe. In the earlier classes, that is from the second law of thermodynamics, you know that the entropy of the system is always increasing. That means the entropy change of an isolated system is equals to or greater than 0 for a spontaneous process. So that is ds is greater than equals to 0. In an isolated system, ds equals to 0 is for reversible process and ds greater than 0 is an irreversible process. We know that generally a system interacts primarily with its immediate surrounding. Thus, the system and its immediate surroundings can be assumed to be isolated from the rest of the universe. Such a system is said to be composite isolated system, and the total entropy change for a system is given by the expression ds total equals to ds system plus ds surrounding. This is equation number 44. And from the equation number 44, you can be rewritten in this form, because we know that ds surrounding equals to dq surrounding divided by t, which is equals to minus dq system divided by t. This is equation 45. We know at constant pressure dq system equals to dh system, nothing but that is dh system. So at constant pressure, at constant temperature and constant pressure, the change in heat is equals to enthalpy change. Therefore, the equation 44 can be written in this form: ds total equals to ds system minus dh system by 2 by t. And simplifying this, we can write ds total equals to tds system minus dh system divided by t, and hence ds total equals to minus dg system divided by t. Since ds total increases for a spontaneous irreversible process, therefore for a spontaneous process at constant temperature and pressure, we can say that minus dg system divided by t is greater than 0, and hence dg system is less than 0. This is the desired criteria for spontaneity of a process under constant temperature and constant pressure condition. That means the change in Gibbs energy should be less than 0. So that is the condition or the criteria for spontaneity of a process under constant temperature and constant pressure. Therefore, for a spontaneous process, the Gibbs energy decreases and the Gibbs energy change for the system is negative. Thus, we can predict the spontaneity of a process based on the thermodynamic properties of the system. For a finite change, the criteria of spontaneity of a process at constant temperature can be given as. So, all these things we have discussed at infinitesimal change, and if we apply the same condition to finite change, then we can write del G at constant temperature and pressure less than 0. So, that is the criteria for spontaneity of a process at constant temperature and pressure. And if del G at constant temperature and pressure is equal to 0, that is the condition at equilibrium. Now, using equation 35, we show that both dH and dTs contribute to the spontaneity of the process. For a finite change at constant temperature and pressure, the change in Gibbs energy is written as del G at constant temperature and pressure equal to del H minus dTs. Del G at constant temperature and pressure equal to del H minus d del S. And again, similarly, there are different combinations of values for del S and del H. Now, in the table that will, so this is the case number 1, where del H is less than 0 and del S is greater than 0, and the condition of spontaneity is del H minus d del S should be less than 0, and hence if del H is less than 0, that means this one is negative, and if del S is greater than 0, minus d del S will be negative, and overall the total value will be negative, and hence in this case the process will be spontaneous at all temperatures and equilibrium is not observed, because the condition of equilibrium is del G equals to 0, but here the del G will be negative, so equilibrium condition is not observed. Now coming to case number 2. In case number 2, del H is greater than 0 and del S is less than 0, and overall this value will become positive, and hence the process will be non-spontaneous at all temperatures. Equilibrium condition will not observe, because the equilibrium condition is del G equals to 0. But here the value of del G will be positive at all temperatures in this case, and hence the process will be non-spontaneous and equilibrium will not be observed. Now coming to the case number 3. In the case number 3, del H is less than 0 and del S is less than 0. So the condition of spontaneity, if magnitude of del H is greater than magnitude of T del S, then the overall value will be less than 0. That is the condition of spontaneity. But for equilibrium condition, the condition is magnitude of T del S should be equal to the magnitude of del H. And using this equilibrium condition, we can find out the equilibrium temperature T equals to magnitude of del H minus, the equilibrium temperature T equals to magnitude of del H divided by magnitude of del S. And the process will be spontaneous at temperature lower than the equilibrium temperature. So if the temperature will be lower than the equilibrium temperature, then this condition will be achieved. This condition will be achieved because this is the condition of spontaneity of the process. Now coming to the next case, where del H is greater than 0 and del S is greater than 0, and the condition of spontaneity of the process is magnitude of del S should be less than the magnitude of T del S. But equilibrium will be achieved if magnitude of T del S equals to magnitude of del S. And from this equilibrium condition, we can find out the equilibrium temperature T equals to magnitude of del H divided by magnitude of del S. And the process will be spontaneous at temperature above the equilibrium temperature. And the next condition, the fifth case, where del S equals to 0 and del G so when del S equals to 0, in that case del G equals to del H, and the process will be spontaneous if del H, magnitude of del H is less than 0, and overall the value of del G will become negative. So the process will be spontaneous only for exothermic processes. But if del H equals to 0, that is the condition of spontaneous equilibrium. And the sixth case, where del H equals to 0, that means del G equals to minus T del S. So the process will be, the value of del G will be negative if the magnitude of del S will be positive. But if the magnitude of del S will be 0, then the value of del G will be 0 and the process will be equilibrium. But for spontaneity of the process, the magnitude of del S should be greater than equals to 0. So the value of minus T del S, so the value of minus T del S will be negative. The entropy must be increased for the process to be spontaneous. Now coming to one example, for a system undergoing isothermal and isobaric process, the change in enthalpy and entropy will be found to be 50 kilojoule per mole and 185 joule Kelvin inverse mole inverse. Will the process will be spontaneous at 330 Kelvin? Calculate the temperature at which the system equilibrium attain equilibrium, assuming that enthalpy and entropy changes are not affected by change in temperature. Here we know that the equation del G at constant temperature and pressure will be equal to del H minus T del S. Given that del H equals to 58 kilojoule per mole, that means 58 into 10 to the power 3 joule per mole, and del S equals to 185 joule Kelvin inverse mole inverse and T equal to 330 Kelvin already given. Now substituting the values in this equation, we can find out del G equals to minus 3050 joule per mole. And as the value of del G will be negative, the process will be spontaneous. After that, we will find out the value. After that, we will find out the temperature at which the system will attain equilibrium. In order to finding that, we know that the equilibrium temperature can be calculated by T equals to magnitude of del H by magnitude of del S. By substituting these values, we can find out the equilibrium temperature is 313.51 Kelvin. But here the temperature is given 330 Kelvin, that means above the equilibrium temperature, and hence that is spontaneous process. But if the temperature will be 313.51 Kelvin, the system is in equilibrium. Now coming to the physical significance of Gibbs energy, because we have already discussed that Gibbs energy or Gibbs function G equals to H minus Ts. Now substituting the value for enthalpy, because we have already studied from the intermediate level enthalpy H equals to U plus Pv. Now putting the value of enthalpy in this equation in place of H, we can write G equals to U plus Pv minus Ts. And again the change in Gibbs energy can be written as dG equals to du plus Pdv plus Vdp minus Tds minus Sdt. And again from the second law of thermodynamics, we can write du equals to Tds plus dw reversible. So the value of dg will be Tds plus dw reversible plus Pdp plus Vdp minus Tds minus Sdt. Now the Tds will be cancelled out. We can write dg equals to dw reversible plus Pdp plus Vdp minus Sdt. Now at constant temperature and pressure, dt equals to 0 and dp equals to 0. And hence dg equals to del w reversible plus Pdv. So this is equation 56. So here the del W reversible is the total work done on the system under reversible condition at constant temperature and pressure. This can include all type of work like electrical, chemical, mechanical work, etc. Now again we know that the mechanical work is the work of expansion or compression and is given by the following expression, that is del W mechanical equals to minus Pdv. Now putting this value, we can write dg equals to del W reversible minus del W mechanical, or dg equals to del W reversible minus del W mechanical, that is equals to del W net reversible work done. As you know that work done by the system is minus del W, therefore minus del G equals to minus del W net reversible. Now again, the system does maximum work under reversible condition, that is del W, the magnitude of del W reversible is maximum amount of work that system can do. Therefore, we say that Gibbs energy is equals to maximum amount of useful work, and that can be obtained from the system undergoing a reversible process under constant temperature and pressure condition. So here we have discussed the two criteria for the spontaneity of the process. The first one is Helmholtz energy and the second one is Gibbs energy. The Helmholtz energy deals with the process at constant temperature and constant volume, and the Gibbs energy deals with the process at constant temperature and constant pressure. And after that, we will find out the relationship between Gibbs energy and Helmholtz energy. Again, we know that H equals to U plus PV and G equals to H minus Ts, that is U plus PV minus Ts. And we know that A equals to U minus Ts. Already we have discussed today. H equals to U minus Ts. So putting these values, we can find out G equals to A plus PV. And let the initial state of the system will be G1, A1, P1, V1 and T1, and the final state of the system be G2, A2, P2, V2, T2. So we can write the equations for initial condition G1 equals to A1, P1, V1 and G2 equals to A2, P2, V2. So the change in Gibbs energy for the following expression can be written as G2 minus G1, that is equals to A2 minus A1 plus P2 V2 minus P1 V1, that is del G equals to del A plus P2 V2 minus P1 V1. And again, from ideal gas equation, we know that P2 V2 equals to nR T2 and P1 V1 equals to nR T1. Now substituting the values from the ideal gas equation, we can write del G equals to del A plus nR whole into T2 minus T1. If the temperature is kept constant, that is T2 equals to T1, we can write that del G equals to del A. So for an isothermal pressure volume change process involving ideal gas, the change in Gibbs energy and change in Helmholtz energy are equal. So these are few questions that you have to solve. Now coming to the properties of Gibbs energy and Helmholtz energy. The first one is temperature and pressure dependent of Gibbs energy. So the Gibbs energy of the system changes on changing the temperature and pressure. Here two possibilities will be there. Variation of Gibbs energy with temperature at constant pressure, and the second one is variation of Gibbs energy with pressure at constant temperature. Let us consider a system undergoing reversible pressure volume change, that is G equals to U plus PV minus Ts. So the change in Gibbs energy is given by the expression dg equals to du plus pdv plus vdp minus tds minus sdt. And again, for reversible pressure volume change, we know that du equals to tds minus pdv. Now putting these values in equation 54, we can write dg in place of du, we can write du equals to tds minus pdv. So the equation 54 can be written like this: dg equals to tds minus pdv plus vdp, dg equals to tds minus pdv plus vdp minus tds minus sdt. So the pdv will be cancelled out and tds will be cancelled out. We can find dg equals to minus sdt plus vdp. Thus, we can say that for a system undergoing reversible pressure volume change, the Gibbs energy change depends upon the temperature and pressure, and this can be mathematically expressed as G equals to function of temperature and pressure. Because from equation 67, we can observe that dg equals to minus sdt plus vdp, and hence The Gibbs energy depends upon temperature and pressure. So G equals to function of temperature and pressure. The change in Gibbs energy in terms of change in temperature and pressure thus can be written as dg equals to del G by del T at constant pressure dt plus del G by del P at constant temperature dt. So the derivative of the first term of the equation 69, that means this one, first term of the equation 69 gives the rate of change of Gibbs energy with temperature and constant pressure, and dt is the total change in temperature. Similarly, the derivative in the second term, that means this one, gives the rate of change of Gibbs energy with pressure at constant temperature, and dp is the total change in pressure. Now comparing the coefficients of dt and dp, that means comparing this one and so this one is the coefficient of dt and this one is the coefficient of dp, because we know that del g by del t at constant pressure is nothing but that is equals to, so these are from Maxwell's relationship. We can write del g by del t at constant pressure equals to minus s, and similarly del g by del p at constant temperature equals to v, implies that the rate of change of Gibbs energy with temperature at constant pressure equals to decrease in entropy. Also, the rate of change of Gibbs energy with pressure at constant temperature equals to increase in volume. Now, let us take up the variation of Gibbs energy with temperature and constant pressure. Second condition. So the variation of Gibbs energy with temperature and constant pressure, that is called Gibbs-Helmholtz equation. So here we will derive the Gibbs-Helmholtz equation. So from equation 69, this is the equation 69. This one is equation 69. dg equals to del G by del T at constant pressure dt plus del G by del P at constant temperature dp. This is equation 69. Now from equation 69, that gives the total change in Gibbs energy when the temperature and pressure change by dt and dp respectively. However, it is always easier to study the variation of thermodynamic properties with change in only one parameter, keeping the rest of the parameter constant. Therefore, we will study the change in Gibbs energy due to change in temperature and pressure. We keep one variable constant and change the second variable. Accordingly, according to equation 167, that means at constant pressure, this one, equation 67, if we take at constant pressure, this term will be vanished. So dg will be equals to minus s dt. And hence we can write dg at constant pressure equals to minus s dt. Now find the total change in Gibbs energy will change in temperature. In order to find the total change in Gibbs energy with change in temperature, we have to integrate the above expression 71 with proper limits. So the LHS of the equation will be integration from G1 to G2 del G, because the free energy, because the Gibbs energy changes from G1 to G2, and similarly the temperature changes from T1 to T2 at constant pressure, and hence the RHS of the equation will be minus integration of T1 to T2 SDT. As the entropy of the temperature, as the entropy is temperature dependent, so it is taken inside the integral, and the integral will become G2 minus G1 equals to minus of integration of SDT from T1 to T2. Since the entropy increases with increase in temperature, the RHS of the above expression will be less than 0. Therefore, we can say that the Gibbs energy decreases with increase in temperature. And using equation 36 and equation 70, so this one is equation 70, and coming to equation 36, The equation 36 is G equals to H minus Ts. So here we are taking combination of equation 36 and equation 769, that is dg equals to del G by del T at constant pressure into dt plus del G by del P at constant temperature into dP. So combining both the equations, we can write G equals to H plus T, H minus TDS. So in presence of minus S, we can write this one. So that will become the equation 73 will become the equation 75. 74 will become G equals to H plus T del G by del T at constant pressure. Now rearranging this, we can write H equals to G minus T del G by del T at constant pressure. Now dividing this equation 75 throughout T square, we can write H by T square equals to G minus T del G by del T at constant pressure divided by T square. Simplifying the above equation, we take a function G by T. In order to simplify the expression, we'll consider a function G by T and differentiate with respect to T. So that means del G by T by del T at constant pressure equals to T del G by del T at constant pressure minus G by T square. Now comparing 76 and 77, comparing both these equations, so both these equations we can write del G by T by del T at constant pressure equals to minus H by T square. This is 78 and known as Gibbs-Helmholtz equation. So this is one long question, that is derivation of Gibbs-Helmholtz equation. So now coming to variation of Gibbs energy with pressure at constant temperature. Again from equation 70, we can take the value del G by del P at constant temperature equals to V. Therefore, we can write del G at constant temperature equals to VdP. Just 1 minute. So therefore, we can write it dg at constant temperature equals to VdP. Now to find out the total Gibbs energy change with change in pressure, we need to integrate this equation 79. So here the integration will be like this: integration of dg from G1 to G2 equals to integration of VdP from P1 to P2. And since volume varies with change in pressure, it is taken inside the integral. So the solution of equation 80 is like this: G2 minus G1 equals to V into P2 minus P1. And again, assuming the gases behave ideally, we can apply ideal gas equation PV equals to nRT or V equals to nRT by P. So in place of V, we can write nRT by P. So the equation 80 will become G2 minus G1 equals to integration of nRT by P dP from P1 to P2, that is equals to nRT ln P2 by P1. As the pressure increased, that is P2 is greater than P1 and the RHS of the above equation will be greater than 0. Hence, for ideal gas, Gibbs energy increases with increase in pressure, and we know that ideal gas under isothermal condition, that is P2 V2 equals to P1 V1, and hence we can rewrite this equation 83 like this: del G equals to G2 minus G1 equals to nRT ln V1 by V2. That means it was nRT ln P2 by P1 that changes into nRT ln V1 by V2. Now coming to an example, 1 mole of an ideal gas undergoes isothermal expansion from 10 liter to 100 liter at 300 Kelvin. Calculate the change in Gibbs energy of the process. Now applying the equation 84, we know that del G equals to nRT ln V1 by V2, which is now converting this natural logarithm to logarithm base 10, we can write LG equals to 2.303 nRT log V1 by V2. So here N equals to 1 mole, R that is the universal gas constant having the value 8.31 for joule Kelvin inverse mole inverse. T equals to given 300 Kelvin, V1 equals to 10 liter, V2 equals to 100 liter. Now putting all these values, we can find out del G equals to minus 5744.14 joule, and hence the change in Gibbs energy of the process will be minus 5.744 kilojoule. So these are few questions that you have to solve. And again, temperature dependence of Helmholtz energy. So similar type of derivation will be there. So here there will be two possibilities. First one is the first possibility is variation of Helmholtz energy with temperature and constant volume, and the second one is variation of Helmholtz energy with volume at constant temperature. Now let us start with A equals to U minus Ts, and again we know that dA equals to du minus dTs minus sdt, taking the derivative of the this equation. And since for a reversible pressure volume change we can write du equal to tts minus pdv. So writing this value of du in this equation 85, we can write dA equal to tts minus pdv minus tts minus sdt. So the tts cancelled out, we can write dA equals to minus sdt minus pdv. And hence from this above expression 86 we can find out the Helmholtz energy depends upon temperature and volume. We can write A equal is a function of temperature and volume. So the change in Helmholtz energy will change in temperature can be written as dA equals to del A by del T at constant volume dt plus del A by del V at constant temperature dV. And from Maxwell's relationship, this one the coefficient of dt that is equals to minus del s, and the coefficient of dv that is equals to minus p. Now coming to the conditions, now take up the variation of Helmholtz energy with temperature at constant volume. So the first condition is variation of Helmholtz energy with temperature and constant volume, that is called Gibbs Helmholtz equation. So from equation 86, we know that dA at constant volume. So if the volume will become, so now coming to 86, here if the here it will take the condition of constant volume, dV will become 0, and hence dA equals to minus sdt. So d at constant volume equals to minus sdt. Now taking integration of the above equation with proper limit, we can write integration of dA from A1 to A2 equals to minus integration of SDT from T1 to T2. So del A equals to A2 minus A1 equals to integration of SDT from T1 to T2. Since the absolute entropy is always greater than 0, this implies that Helmholtz energy decreases with increase in temperature at constant volume. And hence, the Gibbs-Helmholtz equation starting from 21 using equation 89, we can write A equals to U plus T del A by del T at constant volume. Now rearranging, so similar type of derivation is there. Now rearranging the equation, we can write U equals to A minus T del A by del T at constant volume. Now dividing the equation 93 throughout T square, we can write U by T square equals to A minus T del A by del T at constant volume divided by T square. And to simplifying the expression, we take a function of del A and differentiate it with respect to T at constant volume. So we can write del A by T by del T at constant volume equals to T del A by del T at constant volume minus A by T square. So comparing the above expression with equation 94, comparing both, we can write del A by T by del T at constant volume equals to U by minus U by T square. This is called another form of Gibbs-Helmholtz equation. So the derivation, so both the forms are almost similar and the derivation is also similar. Now coming to the variation of Helmholtz energy with volume at constant temperature. So to understand the variation of Helmholtz energy with volume at constant temperature, we can take the condition at constant temperature, that is D at constant temperature equals to minus PdV. From equation 86 you can see, so if the temperature will be constant, dA will become minus PdV. So from this expression at constant temperature, dA equals to minus PdV. Now to find out the total change in Helmholtz energy will change in volume at constant temperature, we need to integrate the above expression. So integrating this above expression, we can write integration of dA from A1 to A2 equals to minus integration of PdV from V1 to V2. And again from ideal gas equation, we know that P equals to nRT by V. So substituting these values in equation 98, we can write A2 minus A1. Solving this one, A2 minus A1 equals to minus nRT integration of 1 by dV from V1 to V2 equals to minus nRT ln V2 by V1, which is equals to nRT ln V1 by V2. So the overall equation will become del A equals to nRT ln V1 by V2, and if we'll consider for pressure, it will become del A equals to nRT ln P2 by P1. Now this is one question. So 1 mole of an ideal gas undergoes isothermal expansion from 10 liter to 100 liter at 300 Kelvin. Calculate the change in Helmholtz energy in this process. So here del A equals to, changing this equation into from natural logarithm form to logarithm base 10. So this equation from natural logarithm change to logarithm base 10, we can write del A equals to 2.303 nRT log V1 by V2. So all the values are given here. So we can calculate the value of del A, that is equals to minus 5744.14 joule. And the change, so this is, thus the change in Helmholtz free energy will be equals to this one. Now coming to the Maxwell's relationship. So these are the Maxwell's relationship. So starting, so in order to find the partial Maxwell's relationship in the partial derivative form, we can recall the equation du equals to TdS minus PdV. So this equation already we have discussed, and that is known as the fundamental equation of thermodynamics. Du equals to TdS minus PdV, and similarly H equals to U plus Pv, and taking differential of this equation 101, we can write dH equals to du plus PdV plus VdP. Now putting this value of du, we can write dH equals to TdS minus PdV plus PdV plus VdP. Now minus PdV plus PdV cancelled out, so we can write dH equals to TdS plus VdP. And similarly from the Helmholtz energy, A equals to U minus Ts. Differentiating this, we can write dA equals to du minus TdS minus SdT. Now again, so writing the value of du, we can write TdS minus PdV minus TdS minus SdT. So the TdS will be cancelled out, and simplifying this, we can write dA equals to minus PdV minus SdT. Similarly, we can write the Gibbs energy expression, that is dg equals to VdP minus SdT. So the expressions 14, 104, 107 and 108 derived above represent the exact differential at the state function. Sometimes these are called the Gibbs equations. So the state functions are, so these are the state functions, and these are also called as the Gibbs equations. So the state function u, that is du equals to TDS minus PdP, that means u is a function of entropy and volume. And similarly, if the state function is h, so dh equals to TDS plus VdP, that means h enthalpy is a function of entropy and pressure. Similarly, a for if the state function is a, that is dA equals to minus PdB minus HDT, that means Helmholtz energy or Helmholtz function is a function of volume and temperature. So if we take the state function g, so the expression is dg minus equals to VdP minus HDT, that means the Gibbs energy equals to is a function of pressure and temperature. So each of these fundamental equations is equally basic and always valid. In a way, these gives four different ways to converting the same information, and from this we can derive out the different Maxwell's relationship. So from this basic four equation we will derive the Maxwell's relationship. Let us consider the first equation, that is du equals to TdS minus PdV. So the first equation du equals to TdS minus PdV. Now differentiating this equation with respect to S, we can write del U by del S at constant volume, because du by so as the volume will be constant, at constant volume this term will be 0, this term will become 0, and we will write du equals to TdS, thus del U by del S at constant volume equals to T. Now differentiating this equation 109 with respect to V at constant entropy, we can write del by del V del U by del S at constant volume at constant entropy equals to del T by del V at constant entropy. Similarly, differentiating equation 14, this one, differentiating this one, 14 with respect to V at constant entropy. If we take constant entropy, so the first term will be cancelled out. So du equals to minus PdV, and hence del U by del V at constant entropy equals to minus P. Now differentiating with respect to S at constant volume V, we can write del by del V del U by del S at constant entropy and again upon constant volume equals to minus del P by del S at constant volume. Since u is a state function, the Euler's reciprocity is valid, and hence we can write del t by, so the Euler's theorem, so that is valid, and we can write del t. So if you compare both these expressions and Euler's theorem, we can write del T by del V at constant entropy equals to del P by del S at constant volume. So this is the first Maxwell's relationship. And similar way, if we find out the second, so this is the second Maxwell's relationship. If we go similar way, so this is the second Maxwell's relationship. And the other Maxwell's relationship, so these are the other Maxwell's relationship. Similar type of derivation will be there. Now coming to Gibbs energy change for a reaction. So if a chemical reaction will be there, the Gibbs energy change, that is defined as Gibbs energy change del G naught. Del G naught is defined as the Gibbs energy change taking place during the formation of a compound in its standard state from its constituent element in their respective standard state at constant temperature. So, if we consider the Gibbs energy change for a chemical reaction, then the standard Gibbs energy change for a reaction is represented as del G naught, and mathematically we can write del G naught equals to summation of standard Gibbs energy of formation of all the product minus standard Gibbs energy of formation of all the reactants. Alternatively, the standard Gibbs energy change can also be written as del G naught equals to del H naught minus T del S naught. And again, the del H naught equals to standard enthalpy of formation of summation of standard enthalpy of formation of all the product minus summation of standard enthalpy of formation of all the reactant. And similarly, the del S naught equals to standard entropy of all the summation of standard entropy of all the product minus summation of standard entropy of all the reactant. So based upon this expression, one question is there: calculate the standard Gibbs energy change of the following reactions at 300 Kelvin using the data. So here C6H12O6 solid plus so this will undergo combustion to form carbon dioxide and water. So here the standard gives free energy of formation of all the reactant and products are given, and here this is one oxygen, this is in the elemental state, so the standard gives energy of formation of all the elements will be considered to be zero elements, and hence we know that standard Gibbs energy change equal to summation of standard Gibbs energy change of formation of all the product minus standard Gibbs energy change of formation of all the reactant. Now putting these values of the reactant and product, we can find out the standard free energy change value like this. And similarly, another question is there. Here you can put this equation, and that is del G naught equals to del H naught minus T del H naught. First you have to calculate the value of del H naught. That is the standard enthalpy of formation of all the summation of standard enthalpy of formation of all the product minus summation of standard enthalpy of formation of all the reactant. And after that, we will find out the value of del S naught, that is entropy, standard entropy, summation of standard entropy of the product minus summation of standard entropy of the reactant. And putting these values, we can find out del G naught equals to del S naught minus T del S naught. So putting this equation, we can calculate the value of del G naught. So all these, so another question is there. So so these are the terminal questions. What we have studied today, you can definitely you can solve all the terminal questions, and here the answers are also there. So so the next unit will so tomorrow we will discuss the next unit. So here we will stop, and tomorrow we will discuss the next unit. Thank you all.